Up next in our exploration of non-relational databases that can integrate with your Hadoop cluster, we're going to talk about Cassandra. Cassandra is a distributed database system that's unique in that it has no single point of failure. There's no master nodes, so it's really engineered for availability above all else. Let's talk about a little bit more about how it works and what's going on under the hood, and then we'll play around with it a little bit and actually integrate it into a Spark script and see how it all ties together. So stay with me and we'll dive in and see how it works. Let's talk about Cassandra. Cassandra is another distributed non-relational database, and the thing about Cassandra is that it has no single point of failure. There's no master node, so pretty clever design there. We'll talk about it in more detail. Cassandra, NoSQL with a twist is what I call it. So basically it has the same underlying data model and data structure as Bigtable or HBase, which we talked about previously, and it's still a non-relational database. So you're still not going to be doing things like joins or normalizing data structures and things like that. It's like HBase, really tuned and optimized for transactional queries, for vending large amounts of data at very large internet-sized global scale. So it's really engineered for high availability, massive transaction rates, high scalability. That's what it's all about. Now it's a little bit confusing because we classify Cassandra as a non-relational database, so sometimes we slap the label NoSQL on top of it. But in reality, Cassandra does have a query language called SQL, CQL. Kind of a cute little play on words there, Cassandra query language. And when you're looking at it, you're like, hey, this looks just like SQL. And in fact, it does. But it's not really SQL because it's very limited in what it can do. Like, you can only do non-relational queries with it. So even though Cassandra does have a query language, we still consider it NoSQL because it is fundamentally still non-relational. It's just, at its core, breaking things up by primary key values and distributing those across a cluster. Cassandra itself, a little bit of a play on words if you want the history of the name. Cassandra apparently is some Greek figure from mythology that can tell the future. And if you think about other Greek figures in mythology that can tell the future, like, I don't know, the Oracle at Delphi, you can see what they did there. Oracle's a popular relational database. Cassandra is a contender for something that can replace it in some applications. So let's talk about what Cassandra's purpose of existence is. Why do they bother to make this thing when we have other perfectly good non-relational databases to choose from? Well, to understand that, we need to understand something called the CAP theorem. CAP stands for consistency, availability, and partition tolerance. And people have proven in papers and whatnot that you can really only have 2 out of 3. Now, to take a step back, there are some caveats around that. I mean, recent advances in technology make that not as true as it used to be, but there's still some truth to that statement. Let's dive into that a little bit more. So consistency, that means that when I write something to my database, I'm going to get the answer back right away no matter what subsequently. So if I have this distributed database system and I write a new value into it, that means that immediately following that, I would expect to get back that result no matter what if I have a completely consistent database. Okay. Now you can actually trade that off by the concept of eventual consistency, which is what Cassandra offers, meaning that if I write a value, maybe it's okay if that new value doesn't actually come back for a second or two. And in a lot of applications, that's the case. Think about social media. If I make a new post to my friends on Facebook or something, is it really the end of the world if everyone doesn't see that immediately? No, it isn't. So that's the case where you might be willing to trade off consistency for something else. Availability. Obviously, you want your database to be reliable and always up and running, and database designs that have a lot of redundancy built in are going to be more available. And finally, partition tolerance means that the database can be easily split up and distributed across a cluster. And that's not true of all database systems, of course. Big, massive Oracle databases, for example, are not very partition tolerant. And unfortunately, you can only have 2 out of 3. And when we're dealing with big data, like we're talking about in this course with a Hadoop cluster, you can't really give up partition tolerance. You really need that in order to distribute your data across a cluster to begin with. So partition tolerance in our context is non-negotiable. So that really only leaves us between consistency and availability to choose from. And Cassandra, its thing is that it favors availability over consistency. So like we said, it's eventually consistent. If you write something into Cassandra, you might not get that value back right away because it might take a few seconds to actually propagate that change throughout the entire cluster. So if you're okay with that, Cassandra can offer you the choice of being more available in exchange for being less consistent. Now, technically, Cassandra is what we call tunable consistency. You can actually specify as part of your query what is my requirements for consistency? How many nodes in my cluster need to agree on a result before I'll accept the answer? So you can actually make your own trade-offs between consistency and availability there. You can say, okay, I'm going to require more nodes to come back with the same answer. And if one of those nodes has a problem, I'm going to fail. Okay, so it's really up to you as a user of Cassandra how you want to make that choice. Let's visualize this whole concept of the CAP theorem and the trade-offs involved here and see where the different databases that we're talking about fall on the spectrum here. So Cassandra, as we said, it values availability and partition tolerance over consistency. So we're saying, okay, we're going to give you the ability to give up consistency and actually deal with eventual consistency, but what we don't want to give up is availability, and partition tolerance is something we just have to have in a big distributed database. Now, the other databases we've talked about are on different parts of this triangle. So let's take a look at HBase. So with HBase, it does have a single master node. The master node does have replication going on for better availability, but at the end of the day, if your master for HBase goes down or a Zookeeper goes down, you're done. And the original Google Bigtable paper actually calls that out as a problem. They do have some availability issues because of that. So HBase can be said to be favoring consistency over availability. Now, to be fair, it's still really, really available. I mean, it's not like HBase is not a reliable thing to run with, but that's the trade-off that it's chosen to make. MongoDB is the same story. And then you have things like MySQL or Oracle, where they've given up good partition tolerance to try to get the best of both worlds on consistency and availability. But distributing that across a cluster is more challenging. So on each side of this triangle, you're seeing the two things that you're gaining, that you're optimizing for, and at the opposite side of the triangle, the thing that you're giving up. And again, with Cassandra, it's more of a gray area because you can actually adjust that trade-off that you want to make as part of the query. So how does Cassandra achieve such high availability at the expense potentially of consistency? Well, it has this ring architecture to it. So unlike HBase, it doesn't have any master nodes that keep track of what nodes serve what data. Instead, it uses what's called a gossip protocol so that every node in your cluster is communicating with each other every second to keep track of who's responsible for what bits of data and where the data is replicated to and whatnot. So every node in a Cassandra cluster is running exactly the same software and doing exactly the same thing and performing exactly the same functions. So your client can talk to any of these nodes to find out where a bit of data lives. And they also talk to each other to communicate, replicating data and making sure that everyone has a backup copy with whatever level of redundancy that you specify when setting up the cluster. So let's think about what happens. So you have a client that wants to write some data, for example. It will talk to a node and that will say, okay, I know that this bit of data gets hashed to a certain value that maps to a given specific node and another node that it's going to back it up to, and maybe even a third one. It depends on how you set things up. So this ring represents the distribution of that data. Basically, the entire range of primary keys that you can write into a Cassandra database get hashed into these different ranges of values, where this node might contain a range of 1 to 1 million, and maybe this is 1 million to 2 million, and so on and so forth. And eventually you come to this wraparound point where you start over again. And these nodes all just communicate with each other, the peer-to-peer, to figure out, okay, how do I copy data around? How do I keep track of changes in which nodes are up and which ones are down? How do I actually keep track of what the fastest node is to go to get a particular answer? So they all just talk to each other, and they use a bunch of gossip protocols, like I said, and technologies like something they call a snitch to keep track of actually how to get to things the quickest way. But it all manages that for you internally. So these nodes all just talk to each other. They manage themselves how to keep replicants of each other and return that back. Now, I talked about the concept of sort of specifying the trade-off you want to make for consistency. So you can actually say as part of your request, I am going to require that I get back the same answer from at least 2 or even 3 or whatever nodes before I'm going to accept that value. So if you're going to be enforcing high consistency, you can say on a read request, I want to get back the value for this key in this database, but I'm only going to accept that value if, say, 2 out of the 3 nodes agree on the same value, or even 3 out of 3 nodes agree on the same value. So that way you can actually make your own trade-off to say, I'm going to actually sit there and wait for these things to become consistent. Or you can say, I don't care. You can say, I'm just going to ask for the first node that gives me an answer back and go with it. And all I really care about is speed and availability. Another thing you can do is a cute little setup like this. So in the context of integrating Cassandra with a cluster, like a Hadoop cluster, you can actually set up separate racks and separate data centers of Cassandra nodes, and Cassandra can be aware of those and actually manage replication between them. So one pattern that's kind of useful is to have one Cassandra ring, one cluster if you will, that is responsible for handling online queries from say a website or a web server. These are all the transactional queries that you might be doing in your system. And maybe that can replicate to another Cassandra cluster that, propagates that same data across. And you can use that for analytics. So then you can use that copy of your Cassandra to integrate with your Hadoop cluster and actually do things like, operate Hive or Spark queries on it to analyze that data in a more batch-oriented system, in an analytics system. So this way you can run big analytics on your Cassandra data without impacting the performance of your transactional system that might be serving a web front end. So that's kind of a cute little trick you can do. Now, like I said, Cassandra does have an API called CQL, Cassandra Query Language. And even though we say Cassandra is a NoSQL database, it does in fact have a query language, but it's not SQL. So at the end of the day, CQL is really just an API for doing reads and writes that are based on primary keys. You cannot do joins in CQL like you can in normal SQL because it is fundamentally a non-relational database. Your data still must be denormalized. You can't do joins, so you can't do like lookups between two tables. So still, it's a non-relational database. And your queries all have to be on some sort of primary key that you've defined on your table. Every table has to have a primary key, and that's how it figures out where data is stored on your Cassandra cluster. It does have support for secondary indices, but primary key is always going to be your best performance. So if you think about it, CQL is SQL stripped down to the point where it's really just a fancy API for doing gets and puts on a NoSQL database at the end of the day. And the reason they've done this is to make it look more like existing database drivers. So you can take an application that was written to talk to an Oracle, or a MySQL relational database, and as long as you make sure that the queries fit these constraints, you can still use that same application code by and large when you move to Cassandra. So it's kind of a cool thing. There's also a tool provided with Cassandra called CQL-SH, the SQL shell, that you can use on the command line, and that's an interactive tool you can use for creating tables, just kind of poking around, seeing what's in there, so useful for administrative tasks. And a little bit of CQL terminology. One difference in Cassandra speak is that they have what they call key spaces. So whereas in MySQL you would talk about a database that consists of tables, in Cassandra you talk about key spaces that consist of tables. They're pretty much the same thing, but just different terminology. Now, Cassandra and Spark can be married together, like we talked about in that example of sort of having your separate analytic Cassandra cluster. I don't want to imply that Cassandra is uniquely suited to Spark. That's not really true. I mean, Spark also integrates well with HBase and MongoDB and MySQL and any database, really, but it is easy to use Cassandra with Spark. DataStax is a company that offers a Spark Cassandra connector. It's free software. And that allows you to look at your Cassandra table just like it's a data frame in Spark. So that's pretty cool. And it's got a lot of smarts under the hood to make sure that when you do queries on the data frames, it gets translated into CQL queries on your Cassandra cluster and does it as optimally as possible. So it's really, really neat in that you can just write code as if it were a data frame and just attach that data frame to your Cassandra cluster, and at that point it's kind of magic. So a couple of use cases for this kind of a scenario. One, like we talked about, is to use your Spark cluster for analytics on data that's stored in Cassandra. And if you're going to do that, you really should have sort of a separate Spark cluster for that that's replicated with your transactional one. You can go the other way as well. So you can also use Spark to transform data that's coming in and store it into your Cassandra cluster for use on the transactional side. So say you have a bunch of log data or sensor data or something like that. You could use Spark to kind of grind through that all and force it into the format that you really need, the denormalized form that you need for your application for a website or something else, and store that denormalized data into Cassandra where it can be vended very quickly to your application. So that's Cassandra in a nutshell. Let's play. Let's mess around with it. So let's go and actually install Cassandra on our little virtual Hadoop node and VirtualBox. And what we're going to do is set up a table for the MovieLens user database. And we're going to write a little Spark script that actually writes into that table into Cassandra and do some queries on it. So let's see how that all works. Let's dive in next.